first speaker is going to be Athina Markopoulou, I hope I'm pronouncing it correctly, from UC Irvine, who's going to talk about work on federated signal maps and ways to collaboratively learn models of signal strength of cellular networks. So Athina, do you want to take it away?
Yes. So the joint I'm presenting today is joined with my student Evita Markopoulou and our collaborators at USC, Jiang Zhang and Kostas Psounis. Next. So we came to this problem because of an application we're looking at. It was how to create accurate signal maps. What are signal maps? They are measurements of performance of cellular networks that operators need. In the past, they used to collect those by driving around tracks and taking measurements. These days, they collect them through crowdsourcing from mobile devices. Next. So we have worked with a number of data sets in that space. For this talk, I'm going to use examples for a data set we collect ourselves on our campus. It's a small but dense data set of a few users over 5 months. Next. However many measurements you have in this space is never enough. So there's a lot of people working on signal maps prediction, mainly how to predict the cellular quality at locations where you don't have measurements based on a number of features. There's a lot of work in this area, including our own. For the rest of the talk, I'm going to consider the simplest problem, which is how to predict RSRP, signal strength, based on location alone, latitude and longitude, using a DNN. Next. So this problem obviously lends itself naturally to crowdsourcing and to federated learning, where multiple devices share their measurements and they collaborate to train a better global model. Next. I don't need to explain to this community what federated learning is. Once we agree what model to train, clients and the server iterate in their local and global updates. Next. And next. So in this setting of federated learning, let me focus today mostly on a single client device. And what is special in this setup is that not all data sit in the beginning on the device, but they come over time. Next. So as the user move around and they follow their trajectory throughout the day, they collect data. So the training data arrive in a streaming fashion. Next. And so let's say day one, this is the location I have been on campus, the light blue locations, and I collect some measurements there. Next. Day two, and next. In this location, I collect this data, and so on. So the data arrive in an online fashion, and what I do with them is a matter of design. Next. So what I decided to do is to base our local updates on the latest interval, on the latest batch of data that they arrive. Next. So in this setup, I'm considering an honest but curious server that observes parameter updates and can compute the gradients or an approximation of the gradients. And the goal is to infer the local training data, in particular the location of the target user. This problem lends itself naturally to DLG attacks, which have been developed in a different context. So deep leakage from gradients have been used to reconstruct training images and training and text. There are a couple of differences in our setting, the most important of which is we're not trying to reconstruct every single location the user has been at, but some sense of average location, which still reveals a lot about the user. Next. Next. All right, so what does a DLG attack look like in our context? The target device has an interval as a batch of data that I show you here in the light blue locations. It does one gradient update, and it sends it to the server. The server has the global model and observes that real gradient update. So it picks a dummy point and it computes the gradient of that point, which we call dummy gradient, and it looks at the difference between the dummy gradient and the real gradient. Next. And it updates the dummy point to match the direction of the real gradient. Next, and next. So at the end of this process, we reconstruct one location for the whole batch. We observed empirically that location is very close to what seemed to be the average location of the points in the batch. Next. And that was true independently of where we initialized the dummy point in that attack. So here I'm showing the different initialization points. They all end up in some central location for that batch. And Emiliano, who was at UCI, may recognize that as the student housing. When we look at this analytically, indeed, the reconstructed location is not very far from the average location. Actually, that distance, under mild conditions, that distance is upper bounded by two terms. The right term has to do with inherent variance in the locations that they are the data points in the batch, and the first term has to do with variance in the gradients. Most of the insights I'm discussing next are related to the second term, the variance in the data in the batch. Next. So as the user moves around, he collects, let's say the day one collected the light blue points. Next, the attacker can infer the average of those locations. Day two, the user moves to these other locations. Next, the attacker infers the average location and so on. Next, and next. Next slide. So depending on the granularity of the interval which we process data, we can get a coarser or finer granularity in the inferred locations. So on the left side, I'm showing you what happens if we operate on weak intervals. So I can only infer a few points. And on the right, I'm showing you what happens if I process my data in batches or rounds of 1 hour. So I can infer more points and I can get more detail. In both cases, I can infer the important location, which here was the home location or the grad student housing, but with a finer granularity, the attacker can do more. Next. So if to formally evaluate the success of the attack, we need a notion of the distance. How far are the reconstructed locations from the real locations? So the real locations are in color, the real locations are in light blue. So we need a notion of the distance of the two. We consider different metrics, and we ended up choosing the Earth mover's distance, because it captures not only the difference in distribution, but how far away in space are the errors. And that's important because there's continuity in the trajectory when the users move. We also consider other metrics, like the percentage of attacks that have diverged. Next. So on the right-hand side, the EMD, the distance of the inferred and the real locations, was 5.3. To put that in context, EMD can vary from 0 to infinity. If you just do random guesses, which I'm showing on the left, your EMD is 21. So the attacker on the right side did quite well. So EMD 0 means they exactly inferred the important location of the user. Next. So the top left graph is the privacy utility trade-off. Utility here is the error in the prediction. The lower the RMSE, the better. And the privacy is captured by the EMD. The higher the EMD distance, the more private. So this is what happens if you do federate SGD, basically one inferred location per batch of data. And that's the best case for the attacker, the worst case for us. Next. As you start to apply averaging that is inherited in federated averaging through mini batches, next, or through epochs, both the error improves and the privacy improves. So you see the EMD slightly improved, and also 55% of the attacks diverged. Next. What you can really do better is by not processing the data in the order they come, because of the continuity of the trajectory. If you process them in the order they come, you help the attacker. Instead, you can manipulate the batch to pick a subset of the data that they are far enough that they break that continuity, so to have high variance in the constructed batch. So that's the idea. It can be achieved in different ways. We had a particular algorithm using clustering. Next.
Athina, we're at time.
Yes.
Can we?
And that helps. Actually, that doubles the privacy and makes 65% of the attacks diverge. And last slide. And I present for the first time a DLG attack for location data. It has difference from the original DLG attack. And I claim that the inherent averaging and federated averaging and simple batch manipulation can provide significant protection here without more sophisticated add-ons. There are a number of aspects I did not cover, and I defer to the upcoming thesis of Evita in the archive for details.
Awesome. Thank you so much. If there's questions, let's hold that to the end. And let's go ahead with the next talk, which is Eugene Bagdasaryan from Cornell Tech, who is going to be talking about location heat maps with distributed DP and secure aggregation.
Hi, everyone. Can you actually do the next slide and just go back to check? Okay, can you go back? Thank you. Hi, everyone. I was just trying to adapt this slide. My name is Eugene. I'm working on the privacy and security. I spent last summer with Google Federated Learning working on this really cool project. So I wanted to share some results from it. Next slide. So we specifically focused on trying to build location heat maps, and kind of over the last couple of years, the location data became really important for monitoring disease and all other applications. But gathering this data is can raise significant privacy risks. So using differential privacy seems to be a really good idea, but differential privacy doesn't only come on the releasing the data, but it's also important when the service providers that aggregates the data also can mitigate its privacy risk. So kind of using like local differential privacy, or what we propose using distributed differential privacy might help to even make the service provider having less problem, less liability for handling the data. So there are a couple of challenges to achieving this goal. So first of all, when you get a lot of data, it's really good to have high accuracy when all the people are at the same place, and you just add a little bit of noise, but the map is pretty accurate. But when some participants are kind of spread it around, and some areas are sparsely populated, and we've been using this New York Times map of location data. I don't know where it came from, but it's kind of one of the articles that gathered all the location data for, I believe it's 20 million location data points. And so you kind of processing this data, you see that there are some spaces which are sparsely populated. So kind of they might be ruined pretty much by adding any noise. And another problem that basically achieving this distributed differential privacy, where you can add less noise, might not work well when you have secure aggregation. And secure aggregation uses the modular clipping, so it's kind of quantization, and some of the privacy mechanisms such as Laplace and Gaussian mechanisms don't work well with modular clipping. So what we worked on and trying to improve kind of current algorithms. So we proposed an adaptive algorithm that was using the hierarchical histogram, and was trying to kind of iteratively expand some of the nodes that are populated more, and kind of keep intact nodes, regions that are not much populated. So kind of making like a hierarchical histogram. But that's also not enough. So a lot of people were doing it, but the problem with this approach that if you don't use secure aggregation, if you just use local differential privacy, regardless of the algorithms that you have, the amount of noise that you need to add to preserve each user's privacy is too much. So what we decided to do as Federated Learning has been using secure aggregation. We also try to use secure aggregation for the analytics, where all the users will contribute noise, and then the final sum only revealed to the user, to the server, kind of making it central privacy, but also distributed kind of privacy by all the users adding the noise. And by just doing this, we significantly improve the performance. But also what we proposed is to schedule the thresholds and privacy budgets for each level. So can you show the next slide? Using our algorithm, where we it's just the iterative algorithms that goes from very coarse level to more fine granular levels. And for each level, instead of picking up instead of picking up the fixed budget and the fixed threshold, the algorithm simply computes the threshold based on the current noise that is added. So the whole point is you just want to cut out all the users, all the regions that have around 0 or like have no users inside, but have a lot of noise added. So you just have a threshold that is above it. And also what you can do for the next level, you can decide on your privacy budget in a way to maximize the signal. And this is also just a simple mass equations that we did by just converting the current number of users in a region. You can decide how much noise they can tolerate. So basically, you want to have it above the average number of users per region, and then you can just that would be your amount of noise that you might tolerate, and then this noise that you can give, you can provide as a privacy budget. So you basically can iteratively increase as the number of users per region goes down because you have more and more fine-grained regions. You increase the privacy budget and you decrease noise, so you get a more accurate result. And so far, the results that we've got, we are really close to even non-private baseline, so just within 5%, and we can outperform just a kind of very naive versions where you just you add noise to all the reported vectors, or even more kind of complex algorithms that use count, mean, sketch, and some other works on adaptive grids and spatial decomposition. However, I would say that count, mean, sketch can also be used to improve the reporting, because we just used one-hot vector reporting with our algorithm, but you can also use count, mean, sketch on top of the algorithm and improve it significantly. All right, I think that's it. Thanks a lot for listening.
Great. Thank you, Eugene. We have a minute left. If anybody has any questions. Okay. If anybody has questions, obviously you can just chime in later and ask Eugene. And I think with that, we'll bring up the next speaker, which is Jay Rowe from Google. Jay is a software engineer and is going to talk about doing FL simulations with JAX. So Jay, you want to take it away?
Sure. Thanks, Sean. Yeah. So next slide, please. So I'll be presenting and introducing something that I've been working on for the past couple months called FedJAX, and this is Federated Learning Simulation with JAX. This is work done in collaboration with Ananda Tirtha Suresh and Ko Wu, as well as many other contributors and collaborators inside of Google. Next, please. So there's a lot of interesting directions that research around federated learning is going in, whether it be algorithms or new tasks or new modeling and things like that, ranging from personalization to new optimization strategies. Next slide, please. And there's a good amount of federated learning frameworks and libraries and tools that are being built to kind of facilitate and make this process easier. Next, please. We'd like to introduce FedJAX, which is something that we've been working on and something that we find really useful. FedJAX is an open source library for developing federated algorithms in JAX. And we think that there are essentially three main parts to FedJAX that make it really appealing and useful. The first is that it's really easy to learn and use. The second is that it comes prepackaged with standard data sets, models, and algorithms that require minimal additional work and can be used straight out of the box. And then the third, finally, is that we have pretty fast simulation speeds. Next, please. Yeah, so in the easy to learn and use, we think that it's pretty easy to learn and use because we actually actively try to minimize and decrease the amount of new abstractions and concepts that you have to learn to start using FedJAX. And we have very simple and efficient primitives that can be used and built on top of each other and composed to make things fast as well as really easy to read and understand. And we also borrow a lot of the, I guess, extremely useful utilities that are originally in JAX. Next slide, please. So if you're not familiar with JAX, JAX is just autograph plus XLA for high performance ML research. So I think that the three main things about why we went with JAX was that it's really easy to use and get started with. It's mainly based on NumPy, and it works out of the box on accelerators. So running your code on GPU and TPU. On the right, it's a really small code snippet for some code written with JAX, where we're just training a really simple linear model. And for the most part, we followed a lot of the patterns and structures we saw in JAX when we were designing FedJAX. So the idea was that if you're familiar with JAX and if you're familiar with NumPy, getting started with FedJAX is super easy. And we'll have a code snippet with FedJAX code in the poster. We just didn't really have time for it now. Next slide, please. Yeah, so the second part was about prepackaged data sets, models, and algorithms. So we have a growing list of prepackaged standard data sets, tasks with data sets and models. Some of these include CFAR 100 as well as Stack Overflow. But in addition to this, we also actually provide tools so that you can create custom data sets and models and run your own custom tasks as you come up with them. And obviously, this list is growing as time goes on and as we get more community contributions. And then here are a list of some of the common standard algorithm implementations we have right now. Next, please. So now we want to go into simulation speed by looking at some common benchmarks. The first one is going to be the EMNIST character recognition benchmark. We actually use the same setup from the adaptive federated optimization paper, mostly because we wanted to map our numbers back to a common task that people are familiar with. And in this case, we are training a CNN with 20 clients per round, 1 epoch per client, and then 1,500 training rounds. And on the right, you'll see a graph where we compare FedJAX speeds on different accelerators. In this case, we're comparing a single GPU versus a single TPU. And obviously, the TPU is a little bit faster, but GPU, you can still run this full experiment with GPU in under 7 minutes and with TPU under 5 minutes, which is quite fast. Next, please. So the next benchmark we looked at was the next word prediction task for Stack Overflow. And again, we are following the setup from the adaptive federated optimization paper. In this case, it's an LSTM, single layer LSTM with 50 clients per round. And here you can actually see a much better speed switch, using a single GPU versus using multiple TPUs. In this case, we're using 8 cores so for the TPU, and you'll see that we're able to actually train this and complete this full experiment in under an hour using the TPU setup. And even using a single GPU, you can still do it reasonably fast, just under 2 hours or just a little bit over 2 hours. Next, please. Yeah, so one interesting question that you might have is, how does this scale as the number of clients increases? And so we decided to take the Stack Overflow next word prediction task and just increase the number of clients and kind of plot how long the average training round duration is. And you can still see that even at something quite large like 500 or 1,000 clients per round, we have like an average training round duration of just over 10 seconds to around, I think it's around like 20 seconds or so. And so that's still quite fast, and this could be useful for DP experiments, for example, where the number of clients per round that are required is much, much larger. Next slide, please. So just some examples for research that's been using FedJAX. For the MIME algorithm, the original authors were able to run a large grid of experiments comparing different algorithms as well as different tasks within, I guess here we say we tuned about 288 configurations in about a quarter of a day. And in the same thing for EMNIST, we tuned about 3,000 configurations or 4,000 configurations in about half a day. So running these sort of widespread experiments with different comparison points of mixing and matching algorithms and tasks is one of the main benefits and key highlights of using FedJAX in our opinion. Next slide, please. Yeah, so if you'd like to get started and learn more about it, feel free to check out our GitHub. And we also have some pretty good introductory notebooks in our Read the Docs page if you're interested in starting to get used with getting started in using FedJAX. And then finally, we have a paper that is actually going to appear in the NeurIPS FL workshop. Next, please. And that's it.
Great. Thank you, Jay. We have about a minute for questions. I don't know if there's any questions.
Okay, I think someone asked. Oh, personalization. Yeah, so we have plans to, so we actually have been working on personalization. We just haven't, I guess like finalized it for external usage. But in terms of personalization, I think actually using FedJAX for personalization now is like entirely possible. It's like very easy. And you should be able to set it up, just from scratch. And I think we actually have an external collab showing an example of training a really simple personalization setup for EMNIST task. And if you drop by the poster session, I can give you the link for that. Awesome. And then, yeah, I guess like recommendation-wise, I don't think we have a single recommendation. You just use the best tool for the task.
Great.
Yeah, I think probably the main thing would be if you're really familiar with JAX and you want to use JAX and also have like a really simple coordination and kind of like, what is it? The way that you write the logic for coordination and training and things like that to be very simple and fast to implement and also fast to simulate. I think that that would be a really good reason to use FedJAX.
I think, thanks a lot, Jay. Those were some good questions. I think we'll move on to the next speaker now. Okay, so next up is Giulia Fanti, who is a professor at CMU, who's going to talk today about looking at ways to do multi-stage optimization of FL.
Hi, everyone. So today I'm going to talk about work that was joint work with Charlie Ho, Kiran Thekumparampil, and Sewong Oh about reducing communication cost of FL through multi-stage optimization. Next. So we considered a pretty standard federated learning setting where we have end clients who are communicating with a central server. And these clients are heterogeneous, so they have local objectives, FI. And here we're measuring heterogeneity by how different the local objectives are, or the local gradients are from the global gradient. Next. So the global objective here is that the server is trying to minimize the average of all of these local objectives. Okay, so I mentioned the heterogeneity here is measured by how different the local gradient is from this global gradient evaluated on f of x. And the clients are periodically communicating with the central server, and our goal is to solve this central optimization using the fewest total communication rounds R. Next. So I'm just going to quickly walk through an example where we have two clients. So here each client has a local quadratic objective, which is shown as the two dotted curves. And the central server is trying to optimize the average, which is shown as the blue curve on the top right. Next. And below, I'm plotting for you the gradients of the local and the global objectives. And the thing I want to point out here is that in the outer yellow regions, the sign of the gradient agrees. So either both are positive or both are negative. And in particular, both are pointing towards the global optimum. Whereas in the central gray region, the sign of the gradients at the local clients is pointing in different directions. And we'll see in a minute why that matters. So next slide. Okay, so remember our goal was to minimize the total number of communication rounds. So a common way of doing this in the federated learning literature is through local methods. So each client takes some number of local optimization steps before communicating with the central server. So here we see an example where each client is taking 4 local steps before communicating. Now, the problem with this approach is that, at least in theory, it doesn't deal very well with heterogeneity. So FedAverage, which is a common local approach, achieves the best known communication complexity only for nearly homogeneous data. So in our example, we can see that as we reach this central gray region, the local steps start moving in different directions, and this can actually slow down convergence to the optimum, which is why these local methods tend to struggle a little bit with heterogeneity. And in fact, follow-up local methods like scaffold are not known to outperform FedAverage theoretically in any heterogeneity setting. Okay, so local methods tend to work better in more homogeneous data. Next. So an alternative approach is to use tools like mini batch SGD, where each client takes a single step single optimization step before communicating with a central server. And this has higher communication cost, but is known to be have optimal communication complexity for high heterogeneity values. And here, optimality is defined with respect to a recent lower bound, which was shown by Woodworth, Patel, and Cerebral. So the situation right now is that we know that mini batch SGD accelerated is optimal for high heterogeneity parameters. And we know that FedAverage is at least state of the art for close to homogeneous data and is optimal for completely homogeneous data. But there's this whole range of heterogeneity parameters in between where we don't know if any algorithm can match this lower bound of Woodworth et al. Next. So the purpose of this work was to try to answer if any algorithm can match. And the answer is yes, at least nearly. And the approach is to use multi-stage optimization. So the idea is simple. We start by running a local method until some heterogeneity-dependent noise floor, and then we'll switch over to mini-batch SGD and run that until convergence. So our main result here is that we can achieve near optimal communication complexity for all heterogeneity parameters by using an instance of this multi-stage framework. And we also observe empirical gains on both convex and non-convex experiments. So this table on the right makes that a little bit more precise. So the first 2 rows of this table show known achievable results for both accelerated mini-batch SGD in the first row and Fed average and scaffold in the second row. And then in the bottom row, we have the lower bound of Woodworth et al. That I mentioned earlier. And the main result of our work is that if we assume that the global heterogeneity is of the same order as the heterogeneity evaluated only at the global optimum, then we can match this lower bound. So that's all I have. Thanks for your time, and I'll be happy to take questions.
Thank you, Giulia.
I have a question.
Yes, please.
Thanks for the great talk, Giulia. So my question is, how do we know when to switch over from the local steps to mini-batch SGD? Do we need?
Okay, great question. So we consider 2 different variants of the problem. One way to do it is that if you know certain parameters that are specific to the problem, like your initial suboptimality gap and your strong convexity and smoothness parameters, you can choose when to switch based on that. However, observing that oftentimes you may not know these parameters, we also look at a multi-stage variant that doesn't require this knowledge. So basically, the idea is that you use step size tuning. So you start reducing your step size, and then eventually switch over to the mini batch approach. So we can talk a little bit more about the details of how you do this switching in the poster session. But we do have a variant that doesn't require knowledge of the problem parameters.
I see. Thank you.
Thanks.
I have a related question. I think in the abstract on the workshop website, you kind of mentioned that this isn't your findings here kind of correlate with learning rate observations of the utility of learning rate decay, and the fact that I'm curious, is this, what's kind of the mapping between the two? Is this always the thing you should do preferable? Is learning rate decay sort of empirical, hack at what is actually you guys are doing explicitly here?
I don't think so. So the reason that we used this approach is because analyzing the learning rate decay is harder to do. So the analysis for this is actually very simple, very clean. But right now, analyzing decaying learning rates at least we don't know how to do it. And as far as we know, the existing literature hasn't been able to analyze that either. But you can think of this as a variant of tuning your learning rates in the sense that, like, when you're running mini batch SGD, effectively your local learning rate is 0. So it's like an extreme version of that. So in that sense, I think we're not able. I wouldn't say that this is like necessarily the right thing to do and that decaying learning rates is the wrong thing to do. It's just that from an analysis perspective, this was easier to analyze. Got it. Okay, cool. Thank you. Yeah, thanks so much, Giulia. I think with that, we'll move on to the next speaker. So Ankit, if you're here. Great.
Yes.
Ankit is a research scientist at Google and is going to talk today about Scalable FL for resource-constrained clients.
Yeah, thank you for the introduction. So today I'll be talking about this recent work, which was basically an intern work performed by Jianwei Wang from CMU. And this is also joint work with Hang, Shashank, Sagar, and Felix from Google, and Gauri Joshi from CMU. Next slide, please. Yeah, so just I think everybody knows what federated learning is. So in the federated learning setting, what we have different clients who have their private data, and this data could be heterogeneous. And then they essentially train a joint model with the help of a server where clients perform local training on their local data. Then they somehow share these updates or the changed models with the server, and server aggregates all these models, and which is again fed back to the clients. So this is the general framework for federated learning, but it somehow assumes that your client has to train the entire model, which could be problematic, let's say, in the resource constraint settings. So where your client doesn't have enough memory or compute power to kind of train the entire model or even store the entire model. So just some examples of these settings are, let's say, large output space or extreme classification, where the number of classes is very large. And then the client can't even store the classification layer, which scales with the number of classes. Or you can think of language models, which are becoming larger and larger to get better accuracy or better performance. So the question is, in this setting where we are constrained by the resources available at the client, how can we perform federated learning? So next slide, please. Yeah, and so one approach to deal with this scenario is this new framework called split learning. So what split learning essentially does, it kind of, as the name suggests, it breaks your model into two parts. So there is a client-side model which stays at the clients, and there is a server-side model which stays at the servers, and you have to somehow do this training jointly for both of these components. But the question is that how to train this split network in a federated setting, and how to make sure that there is communication efficiency while you are doing it. And there, again, just because it's federated learning, so you always have this motivation that how do you ensure privacy guarantees, but this talk will only focus on first two issues, like how to train this model and how to kind of maintain the communication efficiency. So next slide, please. Yeah, so thankfully, there is already a solution for doing this federated learning in the split training setting. The work is called SplitFed. It was proposed by Thapa et al. In 2020. And essentially, this is how their approach looks like. It essentially has 4 key steps. So what happens is that, so each client has a client-side component of the model. So they do the forward pass on their local model or their client-side model, and they pass on the activations, which are denoted by Z here, to the server. And what server does, server runs these activations through the server-side model, computes the loss, and backprop the gradient. And it essentially trains the server component of the model, and then it passes on the gradients with respect to these activations to the clients. And then clients can run the remaining backpropagation and train the client-side model. And now, because we have multiple clients, each of them have their own version of client-side model. So you have to do another synchronization where you are syncing all the client-side models together. So this is all in good. So next slide, please. So essentially what it is ensuring that you can still do federated learning with limited compute and memory, but then there is a disadvantage of this approach. So the disadvantage is that you have to communicate these activations to the server. And if, let's say, each client has a batch size of B and these activations have dimension D, so per client, you have this additional burden of B times D during each iteration. So next slide, please. So what we did in this work, essentially, we proposed a way to deal with this communication complexity issue. So instead of communicating these raw activations to the server, we want to somehow compress these activations and make sure that we can do this distributed training properly. So essentially, at each client, once the client generates these activations, they quantize them using a vector quantization approach. And then you pass on the code book and both the code words to the server. Server decodes them. It gets a proxy of those activations. And then it does the further processing. It runs it through the server side of the model, computes the loss, does the backprop. The issue here is that when it does the backprop, it obtains the gradients with respect to this quantized activation as opposed to the original activation. So you have to perform this gradient correction at the clients to make sure to take care of this mismatch between gradient with respect to original activation versus gradient with respect to quantized activation. So next slide.
I don't know if you saw, so sorry, you have 3 minutes left. Also, you had a question on, does the server have labels to compute the loss?
Yeah, so here in this setup, we are assuming that once you do, so you assume even in the split learning that you have labels. So it could be that clients are also sending their labels, or server may already have access to labels. So yeah, kind of server is assumed to have access of the labels in this setting. So the next slide, please. So yeah, so this was kind of the overview of the proposal. If you are interested in like different components of it and how all things work together, like we can discuss more during the poster session. So here, just to give you some idea how it performs. So we did some experiments on different benchmarks. So for example, here I'm showing the results on 3 benchmarks: Federated MNIST, Stack Overflow tag prediction, and Stack Overflow next word prediction. So if you look at in all of these plot, at the top corner, you have a star mark. That is the performance of the split Fed algorithm, which has this huge communication cost. And red curves are basically our proposal. So basically, you are doing training with our proposed quantization and gradient correction approach. And you can see that you can actually compress this communication between clients and servers quite a lot without losing too much in terms of your performance. So going to the next slide, please. And here we are kind of just doing some ablation study. So we are trying to show, so I talked about this gradient correction step. So the first 2 curves figures are kind of showing the utility of that. So at one place you have lambda equal to 0. That means there is no gradient correction, as opposed to there is gradient correction. And you can see that the degradation of your performance as you compress more and more is much nicer when you have this gradient correction term. And then the rightmost curve is essentially showing, so just to give you what our quantization does, it is essentially some modification of the product quantization. And the last curve essentially shows that our modification leads to better performance. That means you can compress more without losing too much accuracy as compared to vanilla product quantization. And next slide, please. So yeah, with that, I conclude the talk. If you are interested, we can talk more in the poster session. Thank you.
Great. Thank you so much, Ankit. It was interesting. I think in the interest of time, here's a question from Ming Ching. Have you considered having top layers on clients?
No, so we haven't considered that. So yeah, I know that there is this split learning framework where they do this splitting 2 times. So they have like the early network at the client and the top layers at the client and the middle part at the server, so that they don't have to send the labels to the server. But in this work, we do not consider that setting. But I think the same approach could potentially be extended there as well.
Great. Okay, with that, we'll switch to the next speaker, which is Yang Liu from Tsinghua University. She's a professor, and before that was at WeBank, and is going to be talking about FL for larger server models and knowledge fusion. Go ahead, Yang.
Thank you, everyone. Hello, my name is Yang Liu, and today it's my great pleasure to present our work on federated learning of larger server models with selective knowledge fusion. This is a joint work with my intern students, Jie Cheng from Fontaine University and several other collaborators. So there is not a typo. There are actually 2 Yang Lius from my institute currently. So as you can address me with my English name as well, which is Veronica. Okay, next slide. So it is well known that federated learning has several open challenges. First of all, because federated learning places computational burden on edge devices, its learnability is largely limited by the edge resources, on which training large models is often impossible. And to break through model capacity and enable knowledge accumulation is desirable. And other challenges include dealing with device and data heterogeneity across clients, and improving robustness to malicious attacks and communication efficiency, and defending gradient leakage and model inversion attacks. Next. One feasible approach to address the above challenges is through knowledge distillation, where clients and the server transfer knowledge through logs. And there are already some naive KD-based FL approach has been proposed before, which allowed clients to have heterogeneous model structures and achieve better privacy by disclosing only lodges on public dataset, not private models. But these works either assume no model on the server or a prototype server model of the same architecture as the client model. So the performance improvement for a KD-based FL approach is still quite limited. Next. In this work, we first propose a new paradigm to bridge federated learning with a larger server model. We term it FedJAX. By placing a larger server model on a KD-based federated learning framework, we try to address the following questions. Can we accumulate knowledge at the server by learning effectively from fused clients' knowledge? And if so, will the accumulated knowledge on the server help the clients learn their individual tasks better? In other words, will a large server model be mutually beneficial to both server and clients? Next. To illustrate the features of our framework, we compare it with the related studies of a KD-based method in federated learning on the following aspects: whether they use a labeled dataset, whether client models have a heterogeneous architectures, the aggregation strategy on the server, and whether the server has a larger model. And to further prevent negative and malicious knowledge transfer, we design a selective and weighting criteria to enhance our knowledge transfer protocol, termed FedJAX, where S represent selective. Next. So in the proposed framework, during each communication round, our client models first use private dataset to train several epochs, then transfer the predicted lodges on public dataset as knowledge to the server model, who aggregates the client's lodges and then trains with their guidance. Then the server model transfers lodges back to all client models, and each client model distills knowledge from received lodges and continue their training on private dataset. So over multiple rounds, both the server and client models mutually learn knowledge from each other. And next, we propose a selective strategy to enforce the positive knowledge fusion into the larger server model. Specifically, at each iteration, the server model performs self-distillation on the samples it predicts correctly. And for those it predicts wrongly, it retrieves weighted ensemble predictions from the correct clients, where the ensemble weight depends on their entropy, which is a metric of their confidence. The selective module enforces positive knowledge transfer and saves communication at the same time. Next. We compare our experiments results with existing state-of-the-art works. So here, standalone meaning that teacher and the students train themselves, and the centralized all meaning the server and clients perform centralized training on the whole data set, including both public and private data set, respectively. This is in reality, no party has this complete data set, so this can be viewed as an upper limit of the model performance. So it can be seen that our proposed frameworks outperforms all the above KD-based federated learning baseline significantly on both server and client side, indicating that the server and the clients mutually benefit from knowledge transfer, and the framework is able to enhance positive knowledge fusion. Next. And the framework also provides robustness by design. Specifically, we tested 3 different types of model poisoning attacks to evaluate the robustness of our method. By adopting a selective strategy and a larger server model, which is independent from clients, we see that FedJAX provides consistent robustness across various attacks without additional computational cost for the robust aggregation algorithms. Next. And as is discussed before, thanks to the selective strategy, the communication cost of our proposed framework is also the lowest among all the KD-based methods. Next. So here we analyze the knowledge accumulation process at the server. On the left, we see that the self-training indicates that the total number of samples the server model predicts correctly. And the self-distillation and ensemble distillation indicates the number of samples the server learns via self-distillation and client-side ensemble knowledge. So in the initial stage, since both the server and client models learn from scratch, the number of samples that the server model can predict correctly is limited, and most of the knowledge is accumulated by distillation from client model's fusion. As the training progresses, the server model needs to restore some of its knowledge from self-distillation strategy, and the server model continues fusing sufficient knowledge, the number of transformed samples drop to 0. On the right-hand side, we see that the overall performance gradually increase by changing the size of the server model from ResNet 20 to larger models. So the server client models improve side by side. Next. I think I will skip this client slides due to the time limit. So in conclusion, we propose a new paradigm by applying Federated Learning to a larger server model. And then we show that there are several advantages in the unified framework. And the future works may include training even larger models for NLP and other critical tasks. Next. And this is my final slides. So because I'm also involved in the development of a Fed AI ecosystem and the FIT project, so I want to give you a brief introduction. Complementary to TFF, FIT mostly focus on cross-silos Federated Learning applications among organizations. And recently, we documented its main features and performance benchmarks in our newly published paper on GMLR. So feel free to stop by my poster if you have any questions on FIT or my presentations today. Thank you.
Thanks so much, Veronica. And there was one question in the chat. Maybe you can answer it in the chat while we move on to the next speaker. A question about the difference between the public and the private data domain.
It's the public domain.
Yeah, maybe you guys can discuss in the chat or at the poster session if that's okay, and we'll move on to. Thank you very much. We'll move on to Marco Canini, who's professor at King Abdullah University of Science and Technology, who's going to give our last talk on resource efficient FL.
All right, thank you very much, Sharon. Okay, so very excited to be here. Thanks again for the invitation. So today I'm just gonna tell you very quickly about Relay, and you can find more details in a preprint paper on arXiv. This is a joint work with Hamed et al. And Suhaib Akkaust. Next. Right, so as we know, there's been a lot of excitement, a lot of systems that have come out over the recent, really just couple of years, all around getting basically models to train well and train fast in the federated learning setting. And if I were to kind of like summarize all this exciting work, we're either trying to reduce time or we're trying to improve quality via system efficiency gains or statistical efficiency gains in order to improve the time to accuracy at which we can basically call it a day and we have a good model. And so there's various systems that are doing all sorts of tricks and algorithms and improvements, but more or less that is the metric of reference. Next. What we question here, though, is that whether that should be the only metric of reference. And we propose instead a different view in which we put learners in the center, and we ask, what's the cost to get to that model accuracy? Specifically, what is the resource to accuracy? So in this simple experiment here, we had various systems comparing federated averaging, which is very popular. I don't need to introduce it, versus SAFA, which is an approach that doesn't do pre-selection for the participants. So it uses all the participants available, and it distributes training on every learner, and then it aggregates whatever comes back within a certain deadline. And what's specific about this plot is that the x-axis reports the cumulative resource usage to get to a given accuracy, where in this case we focus on the time, the computation time on across all the devices that participated. And so you can see that there is quite a cost to lower the time, which is the annotation above the lines, that can come between using 10 participants in federated averaging could be 8 hours, and you can reduce it to under 2 hours, but that has a great cost. Now, ideally, you would actually, improve SAFA, and we try to plug in an oracle that knows exactly which participants end up not dropping out or end up submitting their updates in time and not being considered stale. But obviously, that's an idealized version. But if you could do that, then you would have reduced your cumulative resource usage to the minimum necessary in here. And provide a fairly competitive resource to accuracy. So the challenge that we have here is that we must balance the count of participants to avoid resource wastage, but at the same time we need to account for resource diversity, which is really the strength of SAFA. Next, so we could turn around and look instead at another system that puts much more emphasis on fast participants in order to really obtain higher or better time to accuracy, which is ORT, recently published at OSDI. And I believe Mosharraf is giving a keynote and is going to probably talk about it. So I'm not going into the details, but the idea of that work is, you want to focus on the devices that can more quickly turn around so that you can gain in terms of time to accuracy. But that is caused at the expense of the diversity of the clients that we're capturing, and thus the rate at which we are seeing unique participants, which can then, in certain cases, in particular in label-limited distributions, it may even compare and fare more poorly than simply a random selection, which could have been better. So the second challenge that we have really is that we must balance fast versus limited availability participants. And so these are the kind of like two challenges that denote the trade-off space. Next, so what we try to do in Relay, next. So what we try to do in this work, Relay, is to take the view that resource efficiency should come as a first principle in the design of the system. So we explore a different point of the design space. And we do two things in particular. One is we aim to increase the diversity of the learners, and we prioritize the learners based on their availability. I'll comment what that means in a moment. Second, we try to boost the statistical efficiency. That is, we allow for updates that are stale to still be considered and aggregated with some weighting mechanism. Once combined, these two techniques allow us to improve resource to accuracy without bringing too much impact on time to accuracy as well. Next. So I don't have all time to describe in details what we're doing, so I'm just gonna guide you through an illustrative example of what we're trying to do with Relay, which I think will convey the point. So what you see here is training duration on a time axis going from left to right. And so, if we didn't do anything, our rounds would be dominated by stragglers. So we're not going to do that. Next, we're going to set a deadline, as it's commonly done in system, whether that is a fraction of participants or it's a hard deadline. And then we're going to call it a day, and we're going to have our round complete. And then the next round comes along. Next. So at the beginning of the round, next. At the beginning of the round, we're basically going to have a model at every device that, informed by its own historical behavior, it's going to be able to try to predict whether or not this device is, how likely it is that this device will still be around at the next round. So if we were not sampled and used at the current round, would the device still be able to participate in the next round? And there is a bit of an exchange between the server and the devices around this. And the server would then select the least available participants with some random shuffling for tie breaking, and it will focus on those. Next. So in this example, we'll find these three particular devices are the least available, and so we're going to select them. And then we're going to wait until the completion of this round. Next. And then by that time, let's say that the orange one has finished. So we'll allow for that update even though it's stale, to be considered and included in the round. Next. And we go on with this approach. And so what the advantage is that this can bring a high diversity of the participants that we can collect. And we specifically pay attention to the ones that would have only limited availability, but possibly high value data that we want to use for training. Next. So I'll just try to convey with some experimental results that this actually works sufficiently well in practice across a range of machine learning tasks, including speech recognition, computer vision, and NLP for various data distributions and across many different configurations. What I want to emphasize is that we're trying in particular to be careful to set up realistic evaluation. So we use compute distributions and network bandwidths and traces of client availability. My apologies, sorry. My wife left me and my daughter. Okay, that's that's COVID. Okay. Apologies. Ahmed, would you be able to take over?
We're just about at time anyways. Maybe I don't know if you want to just.
Okay, so if you put the next slide and that'll be all. So we can basically reach very high accuracy. We can do better than some of the other approaches, considering selection algorithms. Okay, just a second, sorry.
You don't have to worry, Marco. This happens in meetings every day.
Okay, my respirator came back. So we can do better, and this plot is showing that both prioritization and the combination of stale updates help, particularly in the non-IID mappings. Next, and then we can also do better than just stale aggregation algorithms like SAFA, which will be very wasteful in terms of resources. So next. I'm just going to highlight this particular result because this is the one that I'm most excited about. So it's not just putting emphasis on the resource to accuracy, but it's also about the future-proofness of the design, in the sense that we find a lot of these systems, make certain specific assumption about the deployments of federated learning across mobile phones as they are configured today. Right? But what we expect in the future is a larger amount of heterogeneity and more faster devices. So we specifically focus on what would happen as we have hardware advancements and certain percentages of learner get faster and faster. And what we witness is that actually paying more attention to both availability as well as being aware of the staleness of the updates it is further beneficial. Okay. Next. So I'll summarize. So Relay basically takes this view, which is to emphasize the role of the learners so that we can improve in terms of resource to accuracy. And we navigate this complex trade-off between the efficiency and the diversity. And ideally, we really want to strike a good balance between this. We do so by sampling the clients, prioritizing based on their availability, and allowing for aggregation of stale updates. And this has significant benefits in terms of lowering the resource consumption without having too much impact on the time to accuracy. Thank you, and again, apologies for the noise.
No worries. Your daughter just wants to be cited, so you have a collaborator in the making there. Thank you to all the speakers. This was really interesting. We covered a lot of topics: location and privacy, and resource and scalability of FL, and so this was really interesting.